Thank you, Peter. Thank you for the invitation and for the introduction, and thank you all for being here. It's a great pleasure. I will talk about selection and clustering of correlated variables. And some of these, the core of what I'll tell you about is not very recent, but I thought it was the most appropriate topic for this, what I thought this audience would be, and the context that Peter explained to me. But I will also talk about some more recent applications of these ideas. And this was so not all, but most of what I'll talk about is joint work with my student, Xiangrong Zhang, who just now is back in China, and with Rob Nowak, with I think lots of you or some of you know, well, Peter knows him well, particularly. And don't be scared by the number of slides, because I will eventually stop after a finite time. Okay, so just a brief summary. I don't really like to do the summary of the talk because I think it kind of spoils the story, but I'll just very briefly mention that I will start talking about how to deal with correlated variables and why they're problematic in many machine learning problems. Specifically in regression, I will focus a lot in regression, linear regression and logistic regression and generalized linear models in general. Then I'll talk about a specific kind of a way of approaching those problems, how to deal with correlated variables. And I'll talk a bit about theory, about regarding these regularizers. Then I'll move to sort of the orthogonal problem, which is how to solve the corresponding optimization problems when you have those kinds of regularizers. And then in the end, I'll talk about some recent extensions and applications of those methods. And so, as usual, my clicker doesn't work very well. I don't know why. So just to introduce notation and just to make it very clear what I'll be talking about, of course, I'm sure most of you will know these extremely well. This is like statistical learning 101. So we are dealing with a regression problem where you have n vectors of p features or variables, depending on if you're machine learning or pattern recognition person, you'll call it features. If you're a statistician, maybe you call them variables. And we have n responses, and the usual linear regression model is that each response is a linear combination of the corresponding, well, this would be a superscript feature vector with a regression with a parameter beta in the product. So it's a linear combination of the components of xi. The regression coefficients, I'll call them beta. I usually have a little dictionary where I say, well, for statisticians, this is beta. For neural networks people, this is W. For signal processing, this is X. And all the notation is switched around, but I'll stick to beta today. So without loss of generality, which is also there are several ways of doing it. I'll assume that this offset beta 0 is 0. And there's noise. It's often assumed Gaussian by ID, but not necessarily so in general. And so there's a compact way of writing these in vector notation, which is just the vector of responses is some matrix beta, matrix X, called the design matrix, which is obtained by just stacking all those feature vectors and then multiplying by beta and then adding noise. This is a very standard thing. And of course, the goal is to estimate beta from Y and X. So you know the responses, you know the design matrix, you want to estimate the coefficients. You can also do this for other sorts of regression, such as for logistic regression, where your responses are binary. And so the typical model is that the probability that the response is 1 is this sigmoidal function, so the logistic function applied to, again, the linear combination of the variables. And the problem is the same. You want to estimate the regression coefficients from the observations and from the xi's and the yi's. Of course, the same problem. So the general scenario is this. In linear regression, you have this kind of picture. You want to learn a machine. This machine is a linear machine. It just computes linear combinations of the inputs. And in the binary logistic regression case, you have a binary output, which is either 1 or 0. And you want to, again, estimate this. In feature selection, the question is, are some of these variables irrelevant, which is the same as asking, should some beta hats, should some of these coefficients be 0, so should some of these variables be ignored? And another question, which is important, is, are there redundant features? Are there features which are essentially the same? And so maybe we could just use one of them or a few of them. There are many ways, so this is a very old problem in machine learning and statistics, and there are many ways to address this problem. So one type of taxonomy that makes sense and that's been introduced many years ago is to divide these methods into filters. So filters essentially try to find variables that are either redundant or irrelevant, ignoring everything that's going to be done afterwards. So just look at the features and see if they somehow look irrelevant for some reason. Maybe they have maybe the feature is constant, maybe it's obviously irrelevant. There are this could be supervised or unsupervised, in the sense that you can do a filter that uses the labels or a filter that ignores the labels, so it can be done more supervisedly or less. Then there's another class of methods which is called wrappers. And the wrapper is something that's wrapped around some learning algorithm and tries to assess the quality of some subset of features. And I won't go into any details of these. And then there are embedded methods. So the embedded methods, which are the ones that I will be talking about and that people use mostly these days in these kind of settings. So the method, the feature selection is embedded into the learning algorithm itself. And this is typically done by formulating learning as an optimization problem, so as you probably all of you are very well aware of, which essentially tries to find a trade-off between two things. So accuracy, I want my model to fit the data well, and this is usually expressed by some loss, and some sort of desirability. I would like my coefficient vector to have some property that I want to encourage. So for example, do not use irrelevant, be sparse. Do not use unnecessary variables, or have a small norm. Why? Because sometimes when you do this, so when you solve this problem, so you have a loss function, which we'll typically call L of beta, some regularizer. Regularize a way of quantifying undesirability, so the larger R, the more undesirable my parameter vector is. And by doing this, you often get into well-understood, solvable problems. And because you have something which is an optimum of some criterion, that's a starting point for analysis and for being able to say things about the solution of this problem. Okay, so classical choices, let's go back half a century. So the classical choice in linear regression is to say that L is just a squared Euclidean norm of the difference between the responses and the predicted values produced by my machine. And the regularizer can be one of many things. So the classical thing, probably the first one, was called ridge regression, which is just squared Euclidean norm of the parameter vector times some lambda. This goes back at least to Norbert Wiener, maybe earlier than that. Although under this name of ridge regression, it was introduced by Hurl and Kennard in the 70s. And so this is the old classic, and now my clicker doesn't work. I have to move here. Of course, there's the new classic, which is under the name of Lasso, it's from the mid-90s, early 90s by Tibshirani. Of course, it goes back much earlier than this. In the signal processing literature, it goes at least to the early 70s, and there are even some earlier references using L1 regularization. Of course, there's Peter on the audience who wrote this sort of definitive book on Lasso around 10 years ago. So if you want to know anything about the Lasso, it's in Peter's book. So you've probably seen this picture. This is the classical picture that's used to illustrate why the Lasso yields sparsity. These, you can look at these circles as level curves of the loss, which is in this, well, typically they would be ellipsoids, not circles. And these little balls, so this is a ball of the L2 norm, this is a ball of the L1 norm, and what can be shown easily and hand-wavingly is that it is more likely that if you use this kind of regularizer, a ball of the L1 norm, then that these two will meet on an axis, and when they're meeting on an axis, it means that the other coefficient is 0, and so you have a sparse vector, a sparse beta. Oh, damn. Okay. This can also be used, I'm going to move my computer here because my clicker is not working. So I can advance the slides. Sorry. I don't know why this happens. It always happens. Okay. You can also do it for this is very inconvenient now. This can also do it for logistic regression. Of course, it again goes back to the 90s, and it can also do it for generalized linear models. Okay, this is old history. So in many problems, so this is what I'm going to depart from what's old history. You don't want to just identify. You don't just want to identify relevant features, you want to identify all the relevant features. Why would you want that? For example, if you have a gene expression data, where you have typically a small number of samples but many features, many variables, it's very likely that many of these features are highly correlated, and they have a meaning. So when you find features that are correlated, there's a meaning in that because they're, for example, genes that are co-expressed. co-expressed. Or if you're dealing with the fMRI data, you know that are voxels that represent regions of the brain, and they interact with each other. So you want to find these correlations in a regression setting, in a supervised learning setting. So your goal is now not only to do good prediction, but to also identify all the involved genes or variables or voxels or whatever they are. Well, this is problematic for if you're using lasso L1, because this picture exactly exemplifies why, okay? So in a sense, if you have highly correlated variables, your level curves of the squared loss part look sort of like this. So after you normalize and standardize everything, the columns of the design matrix, they look like these, and the L1 balls look like this. So you see that the loss function, you can look at it from this perspective, from the constraints perspective, or from the Lagrangian perspective. It doesn't matter. The loss function is essentially flat in this direction. So you don't know exactly where you'll select. All these points have essentially the same loss in the extreme case, and so this is unstable, and you don't know exactly what you'll get. Depends on the optimization algorithm, where you started, how it works. And so a lot of people have devoted some time, or a lot of time, trying to handle these types of problems. So one approach that has been used is to try to use something called group lasso. So in group lasso, the idea is that you don't penalize the sparsity in terms of individual coefficients, but in terms of groups. So if you knew the groups, you simply would use group lasso, and the problem was sort of be solved. But in fact, in this case, you don't know the groups. That's part of what you want to find. And so there are several approaches. Some approaches use covariance information. Maybe you can extract from your data how much each variable is correlated to the other variables, and then use that information to improve your estimate. And this has been used by different people. For example, Peter has used it in this something, I think it's cluster lasso or cluster representative lasso. It goes by different names. So first you infer these correlations, then you cluster your features, and then maybe use one representative per cluster, or you do something else with those clusters, but you use that information. Another thing you can do, and I'm writing this long expression, but you don't have to look at all the details. This is recent work by Becca Willett and Garvesh Raskuti and some other people, where once you have the correlation, then maybe you can add to your loss function some terms that will encourage highly correlated coefficients to be close to each other. For example, if you know that, say, coefficient J and K are highly correlated, then you have a high weight here. And if they are positively correlated, then the sign is positive. So this term will encourage beta J and beta K to be close together. Okay, so or that is an extension. You can also add the absolute value. And this loss function, and you also have the lasso term. You have everything. Actually, this formulation encompasses lots of formulations of this sort, using different types of variants, different ways of weighting these terms, and there's a lot of work in this direction. So the main feature of these approaches is that the cost is essentially, well, everything is linear in the number of points, because you always need to go through all the points, but it's quadratic in the dimension of the coefficient vector, because you need to compute correlations between each component and all the others. So it grows quadratically, essentially. Okay. So there's another class of approaches to handle these highly correlated scenarios, which is, let's not do anything like this. Let's try to use a regularizer other than L1 that is robust with respect to these highly correlated variables. And the first example of these was the famous elastic net, which I'll show you in a picture in a second. And the second one, not long after that, is something called the OSCAR, which goes for orthogonal shrinkage and clustering algorithm for regression. And the idea is the following. So remember the picture where you have these very flat, where you have the L1 ball and the very flat square Euclidean loss. The idea is to break this kind of symmetry by adding to the L1 ball some other stuff. And in the elastic net, you add the square Euclidean norm, so you kind of inflate the ball out a little bit. It's no longer just a straight line. And in the OSCAR, you add this term, which is, in general, it's the max between the absolute values of all pairs of coefficients. Okay? And then I'll show you what it looks like graphically. So this is probably the most important picture in the talk. So you have these, remember the L1 ball is this inner dashed blue line. So these are the level curves of the loss for a highly correlated case, okay? And the green line is the elastic net, is this thing, so it essentially inflates the ball a little bit out, so it's no longer as flat in that direction. And the Oscar is the level curves of this thing in 2 dimensions is an octagon. And so it has exactly these little vertices there, so it's a polygonal shape. And so what happens is that you may actually hit, the solution may be exactly there. So you have exact grouping condition, rather than just including the 2 coefficients, you will be included in some cases, and they will be exactly equal. Or exactly equal with different signs, okay, if they hit here or here. Okay, and so let me just give you a toy example. This is synthetic data, but it's a real example in the sense that it's the actual solution of the problem. So suppose your design matrix looks like this. So you have these 30 features, and they're grouped. They're exactly replicated in groups of 3. Okay, so if you try to do lasso, you could get these or something else. Lasso would select essentially any convex combination, so the actual group, the active groups were the 3rd and the 5th and the 8th, I think. And you could get these or any convex combination of these would give you the exact same loss, okay? Whereas if you apply Oscar, you get exactly this. Actually, even if beta star was not this, even if beta star was these, you would get groups from Oscar, okay? So there's no, obviously, if the columns are exactly replicated, this is indistinguishable from any other thing where you have the same weight, total weight for that group. Okay? But Oscar identifies that easily. So now there's some real data. So this is proposed by Bondel and Reich in the 2007. So they showed with synthetic and some real, but not very large data sets, that it works well. So it performs typically a little better than elastic net, usually much better than the ridge. But the important thing is the number of degrees of freedom. So you always get lower degrees of freedom, because essentially you're grouping. Some of the coefficients are exactly equal. Okay, so this is the thing. So this is another example. For real data, this is the correlation matrix for some data sets in these plant diversity versus soil chemistry, predicting plant diversity from chemical properties of the soil. And this is an example just to show you that you actually get this. So this is a group. So these 5 coefficients are grouped together, not necessarily with the same sign. So these 4 have the same sign. This has the opposite sign, but they're a group. The absolute values are the same. That's what matters. So these 5 variables are identified as being highly connected. So because they are highly correlated, and so they're essentially treated as one. Okay. Now the next thing was, can we generalize these? And that's the starting point for the rest. Is that yes, we can. So Oscar. So remember what it looks like. It's the L1 norm as usual, and plus this lambda 2 times the sum across all pairs of variables of the max of the absolute values of all of those pairs. This can be rewritten in this way once you notice that the maximum of all the betas in absolute value will appear in p minus 1 of these maximizations. And the second largest will appear in p minus 2, and so on and so forth. So you can write these in this way, okay? This is a linearly decreasing sequence of weights, lambda 1 plus lambda 2 p minus I, where I is going from 1 to p. And then you have to multiply this by the absolute value of the betas sorted in decreasing order in terms of magnitude, okay? So this is the sorting of the betas. And what we did, and also Bogdan did around the same time, this was proposed independently, okay, why we don't have to use this linearly decreasing sequence. Any decreasing sequence would work. Why not use some other decreasing sequence? So we introduced this norm called OWL, ordered weighted L1, which is given by this. Once you're given a set of parameters, which are a non-decreasing sequence of weights, you sort the entries of your argument in decreasing order of magnitude, and then this defines this ordered weighted L1 norm. I'm saying it's a norm, but it can show that it's a norm. you can write it compactly in this way once you define this down arrow as the sorting of the coefficients of a vector. Okay. So it's indeed a norm. It's easy to show that it's indeed a norm as long as the first weight is strictly positive. That's all you need. And all the weights, the others have to be smaller or equal than this one. Otherwise, it's not convex. It has a nice relationship with the one norm. So it has this sandwich inequality with the one norm where it's the one norm times the first weight, and this is the one norm times the average of the weights. So it's sandwiched between these two, which obviously makes clear that if all the weights are the same, this is just the L1 norm. If the first weight is 1 or something, and all the others are 0, this is just the infinity norm. So this is something that interpolates between the infinity norm and the L1 norm. So the infinity norm, which is the maximum of all the absolute values, encourages everything to be equal, okay? And the L1 norm encourages sparsity, so this is something in between. Okay, it has been used after that proposal a few times. So, for example, this is a large-scale machine translation. So this is not neural machine translation. This is essentially a very large logistic regression problem. And this is a PhD. This is from Carnegie Mellon, and they found this is one of the most spectacular examples I've seen in terms of applications. So essentially, I'm not going to go into the details of the experiment. So this translation from Chinese to English, from I don't remember, Armenian to English, or from Czech to English. And what you see is that if you just use sparsity for L1 plus L2, which is the elastic net or OWL, the performance with OWL is always a little better. It's not much better, but what's spectacular here is the number of unique features is much lower when you use OWL. So the degrees of freedom of the model is much lower. So what this is doing is massive parameter or weight sharing, which is something that's known to be useful in neural networks, at least since the early 90s. It's called weight sharing, but what OWL is doing adaptive weight sharing. It's learning what weights should be shared, what weights should be common. And this is a much more recent piece of work this is the work by Rebecca Willett and Garvesh Askuti, which I mentioned, where this is an experiment on doing neural decoding from fMRI data, using correlation information extracted from the data, and then using it to regularize the regression problem using that correlation information, so it's p-squared cost. Whereas when you use OWL, you're just learning on the fly the correlations without having to go through all the p-squared pairs. And essentially you get very competitive results with a much lower cost. Actually, the goal in this picture was not to show that OWL is good, but to show that GTV, which is what they're proposing, is good. But I talked with Beck, and they were surprised that OWL was performing so well without extracting any correlation information. In toy examples, it doesn't perform so well because if you actually have the correlation information, of course, you'll do better. But on real data, it performs, at least in this case, it performs very well, and it's much less costly computationally. So what can we say about properties of this regularizer? So to address this, I'll do a little bit of very simple math, which I found it interesting that it turned out to be useful to handle this problem. So majorization, it's a very old topic. And just to introduce what the words that I need and the nomenclature that I need, let's recall that we have two vectors. We say that one majorizes the other, and it's written like this. If they have the same sums of all the components of the vectors, and all the partial sums of one are upper bounded by the partial sums of the other. So I say that one vector majorizes another if they have the same sum, same quantities, but then the largest of the first is larger or equal than the largest of the other, and the sum of the two largest is larger than the sum of the two largest of these, and the sum of the three largest is larger or equal than the sum of the three largest, and so on. And that's all true for any. So it's like this. So 1, 1, 1, 1 is majorized by 2, 1, 1, 1, and 3. So the more concentrated the same amount is, the less this sequence is in terms of this majorization relation. And if the if both are satisfied, so if beta is majorized by gamma and gamma is majorized by beta, then this means that one is a permutation of the other. And this obviously was created by people who were studying economic inequality, because you can look at these distributions as wealth distributions among a population, the population of 4 people, but of course this is very unequal, this is very equal, and this is where this majorization theory originated. And also this Schur convexity, so we say that we have a Schur convex function when you have one sequence being majorized by the other, implying that this function is less or equal than the function applied to the other. So it's a function that detects the majorization relationship. And we say that it's strictly Schur convex if one sequence is majorized by the other and they're not a permutation of each other, then this implies that this inequality is strict. This is called Schur strict convexity. And in a sense, so Schur convex functions favor more uniform vectors because they have lower values for when the vector is more uniform. It's easy to show that any symmetric function, so invariant on the permutation of the argument that's convex, is Schur convex. Examples, the L1 norm is Schur convex. Of course, it's permutation invariant, but it's not strictly Schur convex. It's also not strictly convex. The L2 norm, for example, and the Shannon entropy are strictly Schur convex. Okay, so I need another notion, which is called the Pigou-Dalton transfer. So what is a Pigou-Dalton? Pigou-Dalton is a bit of social work. We have a sequence of people with some amount of money, and you detect 2 people, say beta I and beta J, where beta I is richer than beta J, and you take some money from the richer and give it to the poor. Okay, but you don't give too much. You don't give an amount that would make the poor richer than the one that was richer. So you make them closer to each other. It's called a Pigou-Dalton also, or a Robin Hood transfer, because it's take from the rich to give to the poor. And so the idea is very simple. So you have these two, you have this sequence of values, all the betas, a vector in RP. You detect one who is larger than the other. You take a little bit from the one that's larger and give it to the smaller one. That's it. You subtract epsilon, you add epsilon, but in such a way that you don't reverse their positions. This is called the Pigou-Dalton transfer. Okay, so now before, when we started working on this, we couldn't find that there was no notion of strong Schur convexity, so as there is for strong convexity. So a strongly convex function that's symmetric is not necessarily strongly Schur convex, and there was no notion of strong Schur convexity, so we defined it, which is we say that a function is as strongly Schur convex in the following way, if the following thing is satisfied. When you produce a vector from beta, you doing a Pigou-Dalton transfer, to just explain the Robin Hood transfer of size epsilon, then the amount of decrease in the Schur convex function f is lower bounded by epsilon, which is the size of the transfer times some constant s. Okay, and that, so it's called, we called it strong Schur convexity by obvious reasons. Of course, strong Schur convexity implies strict Schur convexity, but strict Schur convexity does not imply strong Schur convexity, as is common in convexity stuff. And it's easy to show, well, reasonably easy to show that the owl norm is strongly Schur convex, where the parameter of convexity is the minimum of the differences between 2 consecutive elements in the weights. Okay, so you have these weights that are non-increasing. So for this to be strongly Schur convex, it has to be strictly decreasing, and the minimum step is the parameter of strong Schur convexity. And so the L1 norm is neither strongly nor strictly, we've seen. The L2 norm and the elastic net are strictly Schur convex, but they're not strongly Schur convex, and that's the main difference. That's why the owl will give you exact equality, and the elastic net will not necessarily give you exact equality. And this lemma is the key to the proofs of the following results. So I'll tell you exactly how the proofs are. They're very simple. So in the general case, for linear regression, if you're doing these, okay, then it's easy to show that as long as the Euclidean norm of the difference between 2 columns is less than some quantity that depends on the strong Schur convexity parameter of the norm, then this implies that these weights will be exactly equal. Or if it's the other way around, then they will be symmetric to each other. And actually, both may be true, and then they're all 0. And if you have standardized data, then you can rewrite this relationship using these correlations, these standard correlations. So it just says that if the correlation is high enough, then if this inequality is satisfied, then the two coefficients will be exactly equal. Okay, so there was some result like this in the original Bondel and Reich paper, but it had a lot of conditions which we were able to remove. And then this is also true if you have using L1 loss. It's also true for logistic loss. It's easy to prove. So the idea is very simple, is that if the coefficients are sufficiently correlated, the reduction in the loss that you get by making them different is not compensated by the decrease in the norm. Okay, so the tools are just directional derivatives and strong shear convexity, and it's a very simple proof actually. Okay, so this is again the key thing. Why is this useful? So if you want to use one of those methods that look at the correlations and extract correlation information and then uses it like in cluster lasso or the GTV approach, your cost is np squared because you need to compare all the p squared variables. In this case, I'll show you later, that you can solve any problem involving the owl norm with this cost and p log p. Okay, so it goes down from p squared to p log p, which is for large p is much better. Which is kind of mysterious because you can detect sufficiently correlated things without actually ever computing the correlations explicitly. And of course, and using the responses. So, what can we say about the performance of these from a statistical estimation perspective? So we have a theorem in a paper at the ASTAT a couple of years ago. Let me just explain the scenario. This is the more theoretical part a little bit, so not too much. So the scenario is this one. So we have our observations look like this. Beta star is S sparse. We're assuming it's S sparse. We have working with bounded noise. And we have a random design. So now we are assuming that the rows, I'll show you a picture, of the design matrix are correlated. Rather than the usual thing, which is an identity there, you get C transpose C. Okay? And the idea is that we can write the design matrix where you have correlated columns as an IID, random Gaussian IID, or could be sub-Gaussian, but Gaussian IID, times a matrix that expresses these correlations. Okay? So for example, this matrix says that rows 1, 2, and 3 are the same, and 5, 4, and 6 are the same, but it could be something else. Of course, I'm grouping them together just for convenience of showing. It could be the 1st and the 7th and the 22nd. It doesn't have to be like this. I'm just showing them grouped together just to make it clear that there are groups. Oh, damn, it's annoying. Of course, this correlation is not perfect. It's not exactly repetitions. Then you can have this. So this n by p design matrix, so n samples p variables, is now factored into a squared IID Gaussian matrix times a matrix that captures all the correlations between the variables. So C transpose C would look like this. So this is essentially the covariance matrix of your features of the design matrix. And under those conditions, you don't have to look at all these expressions. Just the key part is just this part here. And if you solve the OWL problem, in this case, it's one way of formulating it, is minimizing the norm of the regularizer subject to some upper bound on the loss. Then you can show that the expected value of the difference, so this is an estimation bound, but under these norms, so actually you cannot get away from having these here because you can only look at those coefficients through the lenses of these matrix C. Then this is all the usual stuff, some other stuff that's specific to this, but the important thing is that you have this usual S log P over N, where S is the sparsity of beta. And it doesn't really matter why. Let me just show you some examples. Standard case, no correlation at all, perfectly IID design matrix, you get the same bounds that you get for compressive sensing, you get something like square root S log P over N, which is very, very classical. So the classical results that have been proven in many different ways by different people in different contexts. The thing that you need, number of samples needs to grow with S log P if you want to achieve a given precision. So there's S, which is the obvious thing. If you have more active coefficients, then you need more data. And log p is the price you pay for not knowing where they are. Okay, there are other analyses of owl and slope by different people, some here at ETH, but they're not focusing on the highly correlated case. They're focusing on another perspective, other scenarios. Okay. So now, if you have a full rank, so you have correlated columns, but not perfectly correlated, so the matrix is still full rank. Okay, then the kind of bound that you recover looks like this. Okay, so you can get out of the C transpose C matrix there, and replace it by a division by the minimum eigenvalue on the other side, and you get something which is very similar to other work by Garvesh Raskuti and other people. So this result does not apply in the presence of perfectly identical columns because lambda mean would go to 0. And it also applies to all bounded. Let me just now show you what happens if you have exactly replicated columns. So suppose matrix C looks like this. So matrix C is what expresses so there are 3 groups. One of the groups have 2 perfectly identical, so this is C, it's not the matrix. It's not the design matrix. And if we denote as beta bar star a version of transformation of beta star, which is a true beta, in such a way that you replicate the coefficients in the group, okay? Notice that if in the perfectly replicated columns, these 2 are indistinguishable. So beta star hat and beta star are indistinguishable. They will give you exactly the same response. So you can, that's an unsurmountable kind of loss of visibility, let's say. In this case, you can show this. You can show the same thing, okay? And essentially, you still have S log P over N, although the vector that you're estimating has a lot more than S coefficients. You don't have S groups, but a lot more coefficients. So you're paying no penalty for this presence of nearly replicated columns. Okay, so this is the essential part of the theoretical results about the estimation bounds for this guy. Now, actually this is more my preferred area, how to solve these problems in terms of optimization, and why is it that you can solve it using P log P cost. So we essentially look at 2 ways of attacking these problems. So you have the loss, you're minimizing the sum of the loss plus the regularizer, or you're minimizing the loss with an upper bound on the regularizer. These are essentially this equivalent in the sense that if everything is convex, then for every instance of this problem, there's a choice of epsilon that the solution of this one is the same as that one. Although it may cost you a lot to find that, because maybe it costs as much as solving the problem itself. And also, if you start from these, it kind of induces some class of algorithms. If you start from there, it induces a different class of algorithms. So we'll look at both. Okay, so essentially we'll look at this. So proximal gradient is the usual thing you use, is the standard thing you use for OWL-T, for the Tikhonov regularization formulation. And we'll look at projected gradient or Frank-Wolf for OWL-I. There's another formulation, which is actually the one that's used in this theoretical part, which is minimizing the regularizer under an upper bound on the loss. It's convenient for the theory, but not so convenient for optimization. So we'll not look at it, okay? So when you have this kind of formulation, there are several methods, but I would argue that this is the standard one today, which is called the proximal gradient. I'm sure many of you are very familiar with it. So it essentially amounts to wherever you are, beta t, you take a step in the negative direction of the gradient of the loss, and then you apply the proximity operator of the regularizer. What is the proximity operator? Is something introduced by Jacques Moreau in the year I was born, which is like this. So you have to find the minimizer of the squared Euclidean norm squared with respect to the argument of the prox plus the regularizer. So this can be seen as a generalization. I'm sure you know about this, or at least some of you. It can be seen as a generalization of projection. If here you had an indicator of some convex set, this would just be the Euclidean projection. So it's some function that's infinity if you're outside the set and 0 if you're inside. Then this would just be the projection on that set. Okay, it would be that. This is just a generalization for generic convex functions. And of course, you also need the gradient of the loss, which is easy because the standard losses are differentiable and easily differentiable, actually. And of course, in practice, you would use accelerated versions of these like Fista or Twist or something like that. Okay? So to explain how the prox looks like, I need two notions. This is, again, a very, it's a nice object, which is called the monotone cone. So the monotone cone is the collection of all the vectors such that the components are sorted in decreasing order. Okay, not necessarily in absolute value, but it's actually in their values. So I'll use that notation. I'll need that notation. The other notation I need is the notion of this permutation matrix, which is the permutation matrix that sorts the vector in descending order of magnitude. I'll call it S. So I said P of U is S if sorted U is S times U. It's a permutation matrix. Okay? So this is it's a long expression, and if I show it all in one flash, you'll be scared. But I'll show it very slowly just to explain why it's very simple to compute the prox. So the first thing you have to do is take your vector, your argument, take only the absolute value, and then sort it in decreasing order. Okay? Then you subtract the weights of the norm. Okay? If you subtract the weights, there's no guarantee that the result is still sorted, because the weights can be the difference between the sorted entries and the difference between two decreasing sequences is not necessarily a decreasing sequence. So the next thing you need to do is to project on this monotone cone. Okay? It's called an isotonic regression problem. I'll tell you in a second how this is done. And then, once you project on the monotone cone, you may have some negative quantities. You need to project on the first orthant, which is just clipping. Everything that's negative, you just make it zero. Okay? Then you undo the sorting by multiplying by matrix P transpose. Okay, you undo the sorting, and then you put back the signs that you removed at the beginning. Okay? So how much does this cost computationally? Well, first of all, how do you project on the monotone cone? Here, how do you do this projection? There's an algorithm, famous algorithm from the 70s, called pool adjacent violators algorithm, which has cost P. So it has linear cost in P. So this is cheap. So the only thing that's expensive, of course, here I'm multiplying by a matrix, so this seems like it would be P squared, but it's not, because I'm just undoing a permutation, so it's just order P, okay? I'm just writing it as a matrix product just for convenience, so it's order P. So the only thing that's higher than that is P log P, because you need to sort, okay? So the cost of computing this proximity operator is P log P. So inside the algorithm, which also has, you need to multiply by matrix which are of size n times P, this is n order n P log P. This is why this is order n P log P. Actually, this kind of algorithm had been derived a little earlier, but not so. The way to derive this, so I'm just showing it, I'm not deriving it. So the derivation is like 2 slides. And there's actually a paper a couple of years before, which is like 10 pages of derivations to reach this algorithm. It's actually quite simple. What about projected gradient? So in projected gradient, it's very similar. The only difference is that you're minimizing the loss with some upper bound on the norm of the coefficient vector. So what you need is to do the same. So you take a step in the negative gradient direction, and then you project again on the ball of the norm. And it was shown around the same time that you can also do that. You can also do that with P log P cost. Should I stop? No. It's 1 hour? No. Okay. Good. So another thing that we did around the same time was to come up with a atomic norm formulation for this, because it's useful for different motives, for different reasons. And just before I do that, let me just remind you what an atomic norm is, for those of you who are not familiar. It's a very interesting and useful concept, which is this. So if you have a centrally symmetric set, what's a centrally symmetric set? So a set such that if a point belongs to the set, minus that point also belongs to the set, that contains the origin. It contains the origin. An atomic norm is something that's called the Minkowski gauge of the convex hull of this set. And it's simply this. So you have, I'll show you a picture in a second. You take the convex hull of the set, and if you want to compute the norm, you just compute how much do I need to inflate this so that I touch the point at which I want to compute the norm. For example, for the L1 norm, the atomic set are these 4 yellow points. Okay, so it's the convex hull of these. It's the blue diamond, the blue square. If you want to compute the norm of some point, you just need to compute how much you need to inflate the ball so that it contains the point. And this for these 4 points, it's easy to show that this is the one norm. There are many, many other examples. It's a very, very, very impactful and very interesting paper by Chandrikazer and Ben Recht a few years ago. And for the OWL norm, it's easy to show that the atomic set looks like this. So essentially, you have vectors that have entries that the first entry is 1 over W1, the second entry, so the second vector is 2 non-zero entries, 1 over W1 plus W2, and so on, okay? And then you need to compute all the signed permutations of those vectors. I'll just illustrate it with a picture. So the atomic norms look like that. So the octagon we knew from the two-dimensional case, and in 3 dimensions, so it looks like that. I don't know why there's a question mark there. And it adds an exponential number of atoms, but it's not a problem actually, in fact, okay? So where is this useful? This is, for example, to do Frank-Wolf algorithm. So in Frank-Wolf algorithm, which is to solve the same kind of formulation that you solve in the constraint case, where you want to minimize the loss subject to some upper bound on the norm, on the regularizer. Okay, this can be done by just computing a vector that has the highest inner product with a negative gradient, but subject to it belonging to this ball. Okay, and then you take a step in that direction with some step size that needs to be selected. It doesn't really matter for us now. What's important is that you can solve if G epsilon W, which is a ball of the OWL norm, you can still solve it with P log P. You can find this vector with P log P cost, and it's essentially the same. Essentially, you need to do the same. You need to take the absolute values and then sort, simplify the problem. Then you look at the highest inner product with B belonging to this set of B, calligraphic B, which is the set of atoms in the first orthant, and which are sorted. So it's a very small subset of atoms. It's only P atoms, actually. Sorry. Here we are. And then you undo the permutation, and you put back the signs, and you inflate the ball. So it's quite easy. So you can do projected gradient, Frank-Wolf, or proximal gradient, all with P log P and P log P cost, okay, without ever having to compute all the correlations between the variables. So finally, I'll tell you about some recent extensions and applications of these. So you can actually extend these to the group case. So if you're solving not one regression problem, but a multivariate regression problem where you don't have one vector of responses, but a matrix of responses. So this is usually written like this. So your matrix B now is a collection of beta vectors, one for each simultaneous regression problems. And the typical thing that you use when you're solving these problems is something called the group lasso, where you sum the Euclidean norms of the columns of matrix B. Of the rows of matrix B, because you're trying to encourage that if a feature is used, it should be shared by all the problems. So the different problems should not be able to solve different features. So different regression problems, they should all share the features that they use, and this is why it's used group lasso. And in the group version of OWL, it's called GROWL, you essentially write the OWL norm, but for the absolute values, for the norms of the rows of the matrix after sorting the norms of the rows of the matrix. So this is the group OWL or OWL. It's also a norm. The proximity operator can still be efficiently computed. It has similar exact grouping guarantees. So it's easy. Just an illustration. So this is the true B. So this is each column of these, because you're solving 5 regression problems in simultaneously. So each of these columns is the beta vector of one of those problems. And we know that rows 5 and 7 are highly correlated. Okay, if you use just group lasso, it will select only one of the rows, either 5 or 7, or maybe some convex combination of the two, whereas group OWL is able to identify that they are highly correlated and select 2 identical rows for the B matrix. Why am I introducing this? Because we used it in deep learning. So everybody's doing deep learning. We want to go to deep learning too. So it's known for a long time, since I mentioned Chen and Hinton in the early 90s, that parameter sharing is good. So it's good to have parameters that share their values, and because essentially you're only estimating one value. But OWL seems to suggest that it's possible to learn which parameters should be equal, rather than just impose it. Of course, there are obvious sharings like shift invariance in convolutional networks. This is not the kind of thing we're after. We're after in something like, say, fully connected networks. Maybe we can simultaneously drop some neurons and detect that some of these features are the same. So this is just a toy, it's just a cartoon to illustrate what the effect should be. We should be able to detect that, say, this connection is the same as this, and this connection has the same weight as this one. So we actually, to make it work, it's a bit more complicated. This is an iClear paper, a CLR paper we had 2 years ago. So the way it works is sort of like this. So we have initialization. We say we train the network using the group OWL norm, because this, of course, is a multivariate regression problem. And then once we have the grouping information and sparsity information, have zeros and groups, we retrain the network, but enforcing the grouping information that was extracted by Growl and the sparsity pattern that was extracted by Growl. And we retrain, and in the end we have a parameter shared sparse deep neural network. Okay? And the results are not spectacular, but are interesting. So with a very mild drop in performance, so this is a very standard problem, MNIST character recognition using just very three-layer fully connected network. It's a very simple model. But we're able to kind of achieve, well, this is good results. The important aspect is this one. So with very mild drops in performance, say from 98.3 or 4 to 98.1 or 0, you get a compression of the network of the order of 20-something, okay? And it can actually be done. The reason why I'm saying it's not spectacular, it's not much better than just using, in this case, just group lasso or group lasso plus L2. It just works in a different way. So, okay, the compression ratio, so total number of parameters divided by the unique values, is essentially the same when you use group lasso and L2 or Growl, but it's achieved in different ways, okay? So essentially, group lasso achieves a sparser network with less parameter sharing, whereas Growl achieves a not so sparse network, but with a lot more parameter sharing, okay? So this is sort of an initial attempt at doing this. We'll see what comes next about this. And the final application I want to tell you about is subspace clustering. So the idea in subspace clustering is you have a bunch of points, and you want to see if they belong to, if they're grouped in subspaces somehow. There are several approaches, but the one that's sort of the state of the art, or used to be, is something by a group of the René Vidal's group in 2013. It's called sparse subspace clustering. The idea is extremely simple and kind of intuitive. If you have a bunch of points, the idea is you're going to regress. You're going to try to regress each point, or write each point as a linear combination of all the others, or most of the others. And if you do that using imposing sparsity, the points that end up being used to represent each point are probably in the same subspace. Okay? That's just the idea behind sparse subspace clustering. Points on the same subspace are likely to be selected. And then once you have these, okay, this kind of gives you a kind of an affinity matrix. You know that points that are selected should, there's the strength with which it was selected gives you an affinity value between those 2 points. So you need to solve big N regression problems of dimension P. Now everything is rotated 90 degrees. And the idea was to replace, why not replace lasso by OWL? Because it will encourage the point in the same subspace to share the same parameter, okay? To have the same weight. And this is just a toy illustration. So you have three, so we are in 3D. We have one dimensional subspace, another one-dimensional subspace, and one two-dimensional subspace. They are not orthogonal. And if you use lasso, so to represent one of the red points as a function of the others, you get this kind of approach. Because with 2 points, you represent any point in this subspace perfectly. So you only need 2, actually. If you use L infinity to encourage them to all, once you have L infinity, which is the maximum of the absolute values, once one coefficient is selected, all the others don't pay any cost to be selected too. So you select a lot of things, but it's not sparsity inducing, so you get lots of noise in the background here. Whereas if you use OWL, and it's a particular version of OWL called OWL ramp, you get tied values because OWL encourages these equal values, and you get a lot more points than here, okay, and the exact zeros there. What is owl ramp? Owl ramp is this choice of weights. What are they encouraging? So owl, remember that the strong convexity parameter of owl was the smallest step size in the weight. So here it's 0. So this is no longer a strongly Schur-convex function. But if you look only at the first R component, it is. So what it is doing is encouraging grouping, but only of the strong coefficients, of the largest. The others are just treated as being with the sparsity inducing this. So it's kind of an owl norm for the R largest values and an L1 norm for the others. So it kind of puts the others down. And so once you compare L1 with owl, this is not the affinity matrix. So the affinity matrix would be this plus this transpose. So these are just the coefficients that are selected. So for each point, these are the coefficients, the coefficients values of this regression for the first point with respect to all the others, for the second point with respect to all the others. And you get almost perfect clustering. You don't need to do anything. You just look at the affinity matrix and you get the solution, essentially. So, just to summarize, so I told you about Oscar, which was the precursor of all of these. And then I talked about OWL, which is a particular, of which Oscar is a particular case. I told you about some exact clustering sufficient conditions, statistical complexity bounds, how to compute everything you need to compute to be able to use these in practice in a convex optimization setting. So proximities, projections, and the linear minimization oracles, all with P log P cost or NP log P. And I've told you about a few extensions and applications. And of course, the question I always get at the end is how do you select, how do you choose these weights? There's work going on in that direction, but not a lot in this scenario of having correlated variables and wanting to cluster them. There's a lot of work on these for other, like for controlling false discovery rate and with orthogonal designs, but it's a different direction. So this is the key question that's still open. Thank you.
Oh, thank you very much. So 57 equals infinity. That's quite a nice thing to remember.
I have more. I have the references.
Okay, no, it's enough. So.
And I have the derivation of the product.
I see.
No, but it's finite.
Okay, but there is a bit time for questions or comments. Any question? And then you raise your hand and I try to throw the ball.
Wow, that was good.
Hi. Great. Thanks for the talk. I was just wondering the generalization from Oscar to all. I understand that you proved things for all and hence for Oscar as well, but do you gain anything statistically if you use, other than a constant factor, if you use OWL versus Oscar, essentially like the best weights compared to the standard one?
For these cases, no, we don't gain a lot, no.
Okay, so essentially I could just use, statistically speaking, I could just use Oscar and, okay. No, otherwise I would have to choose.
For this setting, but in other problems, so for example, there's work by Bogdan and Candes on false discovery rate control, where they have this choice of the W's depending on the statistics of the noise. Okay. And there's also very recent work from last year by Yuel Lu from Harvard on how to choose. But again, not for the correlated case.
So then you would have to choose the W's using some...
And it's asymptotic. Well, in this case, so what we do in practice, if we use this in practice, is use Oscar weights. Yeah. And we do cross-validation because then you only have two parameters. Yeah. Okay. And then you cross-validate those two parameters. Okay. Yeah. Whoa.
Maybe it was for you, so...
I don't have any questions. Well, I have many questions.
Other comments or questions? I actually have one. So it's very interesting and nice that you can capture high correlation. And your theorems also show it related to correlation and in parameter sharing. So in a linear model, somehow the real issue is canonical correlation, right? Whether a group of few variables are linearly dependent, right? And of course, correlation maybe captures the first order phenomenon, but you think it's kind of, first of all, difficult to go beyond correlation, so to canonical correlation? Or is it irrelevant in terms of practice? You think you capture enough with the correlation?
Well, I think it would depend on the scenario. Using these tools, I think we cannot capture canonical correlation. I don't know how much irrelevant it would be. It would depend on the specific problem. I don't know. I never thought very carefully about that difference.
Okay, so actually I should announce first that there will be a small reception outside. I think we go this way, or you can also go that way. So there will be some drinks and things to eat a bit, and you can also chat with Mario. And before we do that, let's thank Mario again for the excellent talk.